Welcome back to MAT1841. So where did we leave off last time? So last time we started talking about some Morse theory. And so we're talking about this sort of continuous Morse theory where you can take a space and we ended with saying that integral lines are either disjoint or the same, and they cover all of your manifold. And the limits and or destinations are critical points. And one of the things that we were going to show is that you're able to partition the entire, you're able to decompose the entire manifold into these manifolds, and these will be called they'll be called open cells, and there will be some sort of cellular complex that allows us to understand the topology of the manifold by breaking it up into these smaller pieces. So where was I? Yeah, what's up?
So is there an easy way to, so these are everyone first and then a gradient to vector field, right?
Yes.
And like if I want to find a stable manifold of some point, there's like all these sorts of like flow lines that converge at that point. So
yep.
Is there like an intuitive way of seeing like how to like, what kind of like cell that they like?
So yeah, a couple of things you could do. Well, one thing you could do is like sort of intuitively, if you have a manifold, one thing you can do is you can just like sample every single point along, or I mean, sample many of the points along the manifold and see where they end up, right? And like assuming you sampled the right ones, it's going to be a bit harder because in order to sample the one-dimensional manifolds, like there are difficulties there. Yeah. But the basic idea is just like, well, intuitively at every point you're going to end up somewhere, yeah. And so you start at every point and see where you end up, and that gives you this decomposition by which points they end up at. Did that answer your question, or? Yeah. Okay, so where was I? Where this is the image of the path, and so yeah, and so one note. I think I have a drawing in my notes, but I'm just going to point it out on my nice prop here, which is that if you look at where everything goes, well, clearly everything goes somewhere, and so the set of stable manifolds. Every single point is on one of our stable manifolds. Every single point can only be on one of the stable manifolds because it can't be on two, because then it have to go to two different places. Since the critical points are disjoint and finite, or I mean, they're separated. And so therefore we know that these sets of manifolds, so in fact, both sets of manifolds, both the stable and unstable ones, and you can like, I mean, it's obviously the same symmetrically. The unstable manifolds decompose as well as the stable manifolds, they also decompose into something called open cells. So both sets of manifolds decompose our manifold, our space, decompose M into something called an open cell. And let's define what we mean by open cell. This is definition 5.15 in the text. And so we're going to say an open D cell, sigma, is a space that's homeomorphic to R to the D. Okay, so in this particular case, if you're thinking about, say, this particular point and all of its, let's say this particular point. I always get stable and unstable mixed up because of whether you're going to climb your gradient or you're going to descend your gradient. But let's look at all the points that come to this point down here. So obviously there are some points that don't. For example, if you're at the very top point, well, you're just going to stay there since it's an unstable critical point base. It's a maximum. So if everything's going down towards like low gradient, well, you're going to have a two-dimensional surface that goes down towards it because you're going to go around, come in from all sides in both dimensions. But importantly, notice that there are several lines that it can't cross. So your two-dimensional manifold, your open two cell, can't cross the interior line here because that's a different manifold. So it can't cross that line, and it also can't cross this line here. That sort of goes around it because that's a different manifold. It can cross. It can't touch the top of that point. Is what I mean. And so somehow there are these missing points, which is what allows it to be homeomorphic to a 2D space. And you can sort of also see it if you look at the manifold that starts here and goes down along both directions. So if you start here and go down, you don't ever reach this point down here. So this point down here isn't part of the unstable manifold of this point. which is why it's unhomomorphic to just the real line, because if it actually touched it, well, then it would be homeomorphic to the circle, which is not what we want. Okay, did that sort of make sense? So you have this decomposition, and it turns out when you do this decomposition, every single one of these the stable and unstable manifolds is actually a space that is homeomorphic to R to the D. And what?
Sorry, like the balls.
What was that?
Why is it not? Because typically the terminology is seen for balls rather than RD, but maybe it isn't.
Oh, sorry. Yeah. So I'm pretty sure this textbook said RD. But if you think about it, that is homeomorphic to the ball of lat shape, right? So you can just contract the space down to a ball, basically. So yeah, I think it is equivalent if you talk about being homomorphic to the ball of dimension D.
Wait, one of them is compact, the other is not. So they can't be.
Oh yeah. Let's just replace this with the ball. So to a ball of dimension D. Because of course everything so it's homeomorphic to a subspace, a subset of RD, a compact, etc. And that is important because we're only working with compact manifolds. So clearly every single one of the decompositions is going to be compact in some sense. Like actually they're not actually compact, because if you look at no, let me replace that. I actually don't think that's the correct definition here to R to the D. Because if you look at this particular manifold, right? So that is actually that is open on both ends. So yeah, so it's an open line on both ends. So it doesn't actually, because it doesn't include that point. Yeah, so it's open, so it's not closed. So it's not a closed line. Yeah. So R to the D. Let's see. Theorem 5.3. The stable manifold S of P of a critical point P with index I is equal to I of P is an open cell. Is an open cell of dimension dim S of P is equal to I. Okay, which is basically which now relates basically the number of negative eigenvalues of the Hessian to the dimension of the stable and unstable manifolds. And this also sort of makes sense because if you think about it, you have some number of positive eigenvalues and you have some number of negative eigenvalues. And I think we called the index the negative eigenvalues. Is that correct? Sorry, like these things are all symmetric. So it's like, so long as you understand which one I'm talking about. But yeah, so basically what you're saying is that the manifold of one of the manifolds from a critical point is based on all of the negative eigenvalues, and the other one is based on all the positive eigenvalues. And the dimension of that like sums up basically. Which also makes sense because if you think about it, you have all the different directions in your tangent space, right? And so clearly, basically half the directions in your tangent space belong to the negative eigenvalues, or not half, but some fraction belong to the negative eigenvalues and some fraction belong to the positive eigenvalues. And those determine the dimensionality of the stable and unstable manifolds. And a corollary of this, which is that the unstable manifold, which is what I just said, U of P of critical point P with index I is equal to I of P is an open cell of dimension U of P is equal to 2 minus I. Or D minus I, where D is the dimension of your manifold. So here we're dealing with 2D manifolds. And let's see. Oh, I have another note here that stable manifolds are pairwise disjoint because they're all just by following the gradient flows. And this just follows from ODE existence uniqueness. You're taking integrals of lines along a gradient field. Yes, and this is actually quite important. Note that the closures of manifolds are not necessarily homeomorphic to the closed ball. So let's goes back to the points that we were making. Because if you take the closure of this line here, the closure of that ends up becoming the circle. And the circle is not homomorphic to a ball. Yeah, so stable manifolds decompose them into open cells. Unstable manifolds are a dual decomposition. And so now, if we illustrate this a little bit more, if we let A and B be critical points, and the dim of S of A is equal to 2 minus dim of U of A. And importantly, if S of A is a face of, so remember that when we were dealing with simplicial complexes, we used this less notation to define so that something was a face of something else. So if this is a face of, if and only if U of B is a face of U of A. Okay, so this goes back to the duality of the decompositions of the stable and unstable manifolds. So if you were thinking about it, when you're looking at the stable manifolds here, this stable manifold is a face of the two-dimensional stable manifold that sort of wraps around and includes everything except for this interior line. And so then this becomes part. This line, this circle inside, not counting the bottom point, is then one of the faces of the wraparound manifold. So as an example, and in fact, in the case of 2D, it's pretty easy to classify. So a minimum has a 2-cell as a stable manifold, and a 0-cell as an unstable manifold. And by 0-cell, I just mean the point itself, of course. And a saddle point as well, it has a 1-cell for both. 1-cell as a stable manifold, and a 1-cell as an unstable manifold. Yeah. And of course, the maximum has exactly the opposite. So 0-cell stable and 2-cell unstable. Okay, so now it seems like we're almost there, right? Because like what we want to do was we wanted to construct a complex out of the, we wanted to have some complex that decomposes our torus here into pieces where the boundaries are lower dimensional manifolds, right? Unfortunately, this is not necessarily quite right. So stable manifolds don't form a complex because it's possible that the boundary isn't necessarily the union of lower dimensional stable manifolds. So it doesn't quite work out. And there's a reason for this. And the reason for this is basically, let me draw it out actually. So say, yeah, so let me see if I can draw this out. So if we have our torus again, so it's upright. So and notice, let's say that we look at this point W here and this point V here. So this is the upright. And you notice that because of the particular orientation, I've put it exactly upright. What this means is that this here, that part is simultaneously, this is the stable manifold of V, right? And it's also simultaneously the unstable manifold of W. And note that B, in particular, B is not a stable manifold by itself. Right? Because the stable manifold of V isn't just V, it includes like another like circle. And so therefore, if you just take the set of stable manifolds for all the critical points, that doesn't actually form a complex because it's possible that the boundary isn't the union of lower dimensional stable manifolds of critical points. And this is a bit of an issue. And this is the reason why we can't just use these stable manifolds as our cellular complex. Notice how, so we're going to define something that's a little bit more restrictive than just the Morse function. This is definition 5.16. So a Morse function is a Morse-Smale function if the stable and unstable manifolds intersect only transversally. So, and let me just write this out. So transversality implies that the intersection of a stable Q manifold, intersection of a stable Q manifold. Sorry, my handwriting is really bad today. Tell me if you can't read it. I apologize. I don't know why it's so bad today. Usually not this bad, I don't think. A stable Q manifold and an unstable P manifold has dimension Q plus P minus D. What do we really mean? What we really mean is that when the manifolds cross, they don't like line up perfectly. In 2 dimensions, that's precisely this case where the unstable manifold is also, in 1 dimension, let's say where you have 1-dimensional manifolds intersecting. What you mean is that when they cross, you get a 0-dimensional manifold. They only cross at a point. Obviously, for higher dimensions, if you have 2 different planes, then generically they cross in a line, right? As opposed to somehow crossing in a way that gives you an entire plane. And you can get higher dimensional analogs of this, but basically you don't want them to cross in some special way where they have to be lined up. Because if they cross in that sort of special way, you get weird stuff that happens, like you saw with this case where it was exactly the upright torus. So note though that generically this doesn't happen, because generically things don't line up. So when we talk about generics, we're talking about most of the time somehow things don't line up perfectly. And so generically this doesn't happen. This doesn't happen. And in fact, for the upright torus, there's actually a really easy way of fixing it, which is we just do this. So if you just tilt it slightly, then it no longer becomes, you no longer get this very special lining up of the unstable manifolds. And then the unstable manifolds of these things do cross in a point instead of being exactly on top of each other. And once you do this, so once you have a Morse-Smale function, then that implies that for a Morse-Smale function, the boundaries are actually unions of lower dimensional things. So the boundary of a of a stable manifold is a union of lower dimensional stable manifolds. Okay, so in some sense, what we're doing when we're defining these Morse-Smale functions is we're trying to be as generic as possible for a smooth function. Like, I mean, it's not rigorous exactly, but what we're trying to do is we're just saying that generically things don't go too wrong. And most of the time, when you have these manifolds and they cross, you end up in a point. And that is the only case we're going to consider for these Morse-Smale functions. And the other thing you can do is, since these stable and unstable manifolds cross transversally, you can define a new complex that includes both the unstable and stable manifolds. And so that's exactly what we're going to do here. So this is definition 5.17, which is the connected components of sets UP intersect SQ for all critical points P and Q on the manifold. These are called Morse-Smale cells. Okay, and of course, and once you do this, we can give these things specific names. So for a self-dimension equal to 0, we call these things vertices. If we have a self-dimension equal to 1, we call these things arcs. Dimension 2, we'll sometimes call these things regions, and so on. And then the collection of these things, the collection of Morse-Smale cells forms a Morse-Smale complex. And now we have a cellular complex, we can talk about homologies in the same way that we did when we had a simplicial complex. Because we still have a boundary operator. We have a boundary operator, and that means we can get chain groups and chain complexes and so on. And here this is going to allow us to define something that's called the Floer homology. But first we need to define everything in this context. So we're going to define chains again. So more precisely, if we let K be a Morse-Smale complex, well, let's define a Q chain as a formal sum, just like we did with simplicial complexes. Formal sum, and here we're taking a formal sum of the index Q critical points. Of index Q critical points, the sum over CQ sigma Q, where CQ is in F, and the sum is taken over all possible index Q critical points. Points sigma Q in K. And the set of all Q chains, this is of course a vector space. Is CQ of K. And of course, often for computation, we let the field that we're taking this over just to be equal to the field of order 2. And now we can give a boundary. So we have a boundary operator. So what's the boundary? The boundary of an index Q critical point, Q critical point, U is the sum of the index Q minus 1 critical points connected to U by an edge in the complex. There's a slight difference here, which is sometimes you'll be connected twice. So if there are multiple edges, we add the index Q minus 1 point multiple times, which we didn't have to worry about with simplicial complexes, but we do have to worry about for these cellular complexes. But still, this gives us a boundary operator, and you can basically take a formal sum of all the critical points on your Morse-Smale complex. Oh, sorry, I have to tilt this slightly for it to be a Morse-Smale complex. You take a formal sum of them, and each of these are connected to all the other critical points by some number of edges in the Morse-Smale complex, and that gives you the boundary operator. Yep, and so where the index is, you're looking at basically the stable manifold that's associated with it, and that's the sort of dimensionality of the shape you're looking at. And so this gives us a chain complex. So chain complex, which is of course just you have this boundary operator, and you do all the usual things. And homology groups and Betty numbers are all defined the same way. And once we do this, we get some Morse inequalities, which is that if we have some manifold, so if we let some M be a manifold of, so I'm now going to move away from talking about this in just the 2D case. I'm just going to write about it in the generic case. So we let this be a manifold of dimension D, and we have some function f from M to R, a Morse function. A Morse-Smale function. Actually, I think this might be true for all Morse functions. I don't quite remember. And we let CQ be equal to the number of critical points of index Q. So the number of critical points. When there are a couple useful facts. So first, we have the weak Morse inequalities, which is that CQ is greater than or equal to the qth Betti number for all Q. We also know that the strong Morse inequality. So if you take the sum over all Q equals 0 to J minus 1 to the J minus Q CQ, that's greater than or equal to the sum over Q equals 0 to J of all the alternating sum of the Betti numbers for all J. So this is basically relating the indexes of these critical points to the Betti numbers of the underlying space. Also that the second strong inequality, the second bit, the strong inequality is actually an equality for the sum all the way to D, where D is the dimensionality. That's actually equal to the sum over Q 0 to D of the alternating sum of the Betti numbers, Q minus Q beta Q of M. And what is that again? So what's the alternating sum of the Betti numbers of the space? Yeah, so it's just the Euler characteristic. And so it turns out that you can compute the Euler characteristic by just looking at the number of critical points of each index and taking the alternating sum of those numbers. So this is just the Euler characteristic. Okay, and it's possible to show some relationship between the homology that we just defined and of course the singular homology of the space itself, and so therefore this is one way of understanding the homology of the space. So what we're basically saying is that we can understand something about the homology of the space by just looking at the homology of its decompositions with respect to a generic function. So we started with just the space, we imposed some function on it that happens to have some nice generic properties, and then all of a sudden we understand a decomposition of the space as well as the homologies. But now we have another problem, which is that looking at these sorts of really nice functions doesn't get us quite what we need to do for actual data analysis, right? So often the functions that we get in practical situations aren't actually smooth. So they aren't perfectly smooth. We don't, and so we need to extend our Morse theory to include at least some non-smooth functions. And for that, we're going to deal with a set of piecewise linear functions. Piecewise linear functions. And here we're going to go back to like a triangulation of our space with a simplicial complex. And what we're basically going to say is that instead of having a function that's defined on the entire manifold, you can just define a function based on its values on a simplicial complex or a triangulation of your manifold. And we'll get basically the same results. And so let's start getting into something a bit more discrete. So let's see. I'm going to define something called a Lowerstar filtration. Star filtration. So if we let K be a simplicial complex, so we're back in combinatorics then but what we're going to do is for our simplicial complex, we're going to assign a value for each of the points. So with real values at all vertices. Okay. So then what we can do is we can linearly extend. We can linearly extend to get a piecewise function, a piecewise linear PL function f from, I'm going to use the double bar around K to refer to the simplicial complex geometrically. Since remember, we defined simplicial complex a couple different ways. We had this abstract simplicial complex that was just defined as some set of sets of the vertices. But you can also think of it geometrically as a collection of, well, these simplices in your space. And what we want to do is we want to extend our function, which we've defined on each of the coordinates, to a function that is on every single point in our simplicial complex. And this is going to be defined by a linear extension by f of x is equal to the sum over I, bi of x, f of ui, where ui are vertices, these in K, and our bi of x's are the barycentric coordinates. Centric coordinates of x. What do we mean by that? Well, we just mean that suppose that this is our simplicial complex. Let's say this is our 2 simplex. We have a point u1, u2, u3, and we put values on each of those points. And then all we're saying is that the value at this point here, value there is the weighted sum. Value is weighted sum of the vertex values, depending on how close you are to the vertex. So there's just a linear interpolation of the vertices to get this piecewise linear function over the entire simplicial complex. Again, we're going to assume that f is generic. Assume f is generic. So there are no special things that line up, basically. And if there are no special things that line up, and one of the implications is that all the vertices have different values, right? So if you were to randomly assign values to each of the vertexes, well, you wouldn't end up getting 2 vertexes that have the same value with any measurable probability. And so for the generic function, we can assume that we can give a full ordering on all the vertices precisely by the values of the function f. So can order vertices f of u1 is less than f of u2 is less than all the way through f of un. Okay, so now that we've done that, we can define a subcomplex. So we can define a subcomplex Ki. So define subcomplex Ki by taking just the first I vertices. So if you're thinking about this as some function that you've defined on some shape that you've triangulated, what you're saying is that as your function value goes up past a vertex, you're including all the vertices below it. And I'll draw that out in a moment. So this is to say sigma is in Ki, if and only if, well, sigma has to be in K since it's a subcomplex. And for all uj that are in sigma, j is less than or equal to I. So all your vertices are present. So we're going to define a couple terms. I probably should have defined when we introduced simplicial complexes earlier, but I forgot to. So the star of a vertex is, let's say a vertex ui is the set of vertices, is the set of cofaces of ui in K. And a coface is just some other simplex that ui is a face of, so that ui is in. So star of ui is equal to the set sigma in K such that ui is in sigma. And now we can define a Lowerstar because we're trying to define this thing called the Lowerstar filtration. So the Lowerstar of a vertex ui is the subset of simplices for which ui is the vertex with minimum function value. Okay, so what we're saying is that this is all the simplices where ui is the bottom vertex. So if we write this out, a star lower of ui is equal to the set sigma in star of ui such that x is in sigma implies that f of x is less than or equal to f of ui, or for vertices. So now note that because we're generic, each simplex has a unique maximum value, unique maximum and minimum value, and thus belongs to a unique lower star, which implies that the lower stars partition K are a simplicial complex. And furthermore, we know that Ki is the union of the first I lower stars. Okay, so now that we've defined all this, we can define the lower star filtration. So the lower star filtration, is the nested sequence of complexes. The empty set is contained in K naught, is contained in K1, is contained in K2, and so on, up to Kn, which is just equal to n. And now, of course, so we've defined a simplicial complex. And the important thing to notice is that these Ki are representative of the sublevel sets. So remember, when we were talking about Morse theory, we were talking about the sublevel sets as all the stuff that was below a particular value of the function. So we're thinking about intuitively as some height function. As you go up, it's all the stuff that's below it. And we can do the same thing. And it turns out these Ki's completely characterize all the sublevel sets of the simplicial complex. And the reason for this is, so Ki are representative of sublevel sets. K, the simplicial complex of Ka, which is equal to the inverse of the function. So for everything from minus infinity to a. And this is because suppose that f of ui is less than or equal to a is less than f of ui plus 1. When the sublevel set and Ki have the same homotopy type. Okay, well, let me draw that out a little bit more. So let's suppose we had some simplicial complex. Hopefully I'm drawing this generically enough, but I might have messed it up. And let's say I have this and that. Okay, so let me give me a little bit more space. Okay, so suppose we have some simplicial complex that looks like this, and we're looking at the sublevel sets underneath some line here. Well, then what you can do is you can just retract each of these down, because if you think you can track them down, that doesn't change the homotopy type because you're not changing any holes. So you're retracting each of these edges down, and you're retracting that entire simplex down to you're retracting all of these things down, and that doesn't change the homotopy type, right? So once you've retracted all of these things down, then whatever the maximum item here, which I think is this one here, so that has the same homotopy type as k sub I for that value. So you can shrink down any partial simplices that you have. And therefore, you can think of these this Lowerstar filtration as, if you think about a triangulation of your manifold, you can think of this Lowerstar filtration as precisely getting all the different homotopies of the all the sublevel sets. And this is easier, right? Because now you have a fixed number of points that you have to be looking at the homology of, rather than, of course, well, all possible sublevel sets. So let's define a couple other things. So if we define the closed, I am running out of time, but I think I'll just finish in time. So the closed star, st u sub I, closed of a vertex ui in simplicial complex K is the smallest subcomplex. The smallest subcomplex of K that contains the star. And note, of course, that's because the star of a node doesn't include all of the subbases of that. And so this is basically taking the star and then taking all the subbases in such a way that you actually get a subcomplex. And once you've defined the closed star, you can define, well, everything that you've added. So the link of a vertex is, well, it's basically everything that's in the closed star minus, well, everything that was in the star itself. Okay, so these are all the different things you've added. And we can also define a lower link because we defined the Lowerstar. So the lower link is the Lowerstar of, okay, so it's just everything that's in the closed Lowerstar that's not in the Lowerstar itself. But so now what happens as you go from Ki minus 1 to Ki? Well, when you're going from Ki minus 1 to Ki, what you're doing is you can think about it as attaching the closed Lowerstar of Ui and gluing it along the lower link to the complex. So you're basically adding all the stuff that you're missing from to the next level. And so, so basically the lower link is what you're adding each time. The lower link of a vertex is what you're adding each time as your function increases in value. And we can use that to define a concept of a vertex being regular or critical. So remember, when we were talking about this in the context of sort of continuous Morse theory, we talked about a vertex being regular or critical based on, well, the Hessian matrix and the whether or not, based on the first derivatives, and whether those are all equal to 0. So as in standard calculus. What we're going to do here instead is we're going to define it whether or not a point is critical by the homology of the lower link. So as you cross that boundary, you cross that vertex by including it, that lower link is what you're pasting on top. It's what you're gluing to the existing complex. And you're asking, how trivial is the homology of the thing you're pasting? If the thing that you're pasting doesn't change the homology at all, well, then it's regular. If it does somehow change the homology, then it's critical, basically. So let me write that out a little bit more formally. So if the lower link of UI is non-empty, but homologically trivial, then we're going to call UI a PL regular, piecewise linear regular vertex. Okay, and note that the assumption of genericity is important here, because what you don't want happening is you don't want, as you increase your value, to include two vertices at once. Because if you included two vertices at once, even if they both have lower links that are homologically trivial, if they're not connected, well, then you just have two dots, and so that's homologically, well, non-trivial. But as long as you can ensure that you only add one lower link at a time, well, if you just basically add a ball onto something, it doesn't actually change any of the homology. Alternatively, if the lower link has the homology of a Q minus 1 sphere, then UI is a simple PL critical vertex of index Q. Okay, so this is a little bit harder to understand, but basically what we're doing is, what we're saying is that when you add on, if you're in the case where you have a piecewise linear function and you have this generic condition, then the only things that happen, and actually I should write this down. So let me write this down and I'll explain it. So a piecewise linear function linear function f from the simplicial complex to R on a manifold is a piecewise linear Morse function if each vertex is either PL regular or simple PL critical. And the function values are distinct. F values are distinct at vertices. Okay, so basically what we've now done is we've defined an analog of Morse functions for the sort of discrete case. And the way we do that is instead of measuring the dimension of the unstable or stable manifolds, we're effectively doing that by looking at the homology of the lower link, that you're adding onto it. And in most cases, you're going to get something regular, so you're going to add stuff that doesn't actually matter. But occasionally you're going to add stuff that does matter. And the claim is that in the generic case, for what we're going to call a PL Morse function, you're going to add something that has the homology of a sphere, or a circle, or a sphere. You can have more complicated cases, but if you had a more complicated case, then it's suddenly no longer this easy classification. And so we're only going to deal with these simple cases for the PL Morse functions. And now that we have this definition of critical points with an index, then all of a sudden, everything that we talked about with Morse theory in the sort of continuous case, we can prove analogs of them in the sort of discrete case for the piecewise linear functions. So for example, one thing we can get is we get the Euler characteristic, again for free. So if we have the Euler characteristic of K, that happens to be equal to the sum over U for -1 to the index of U. So alternating sum of PL critical points. And all the PL Morse inequalities also hold. So the inequalities that we had earlier for the Morse theory, for Morse-Smale functions, those also hold when we have this piecewise linear Morse function. Yeah, so more precisely, if you have if you have a triangulation of a manifold of dimension D, and you have some piecewise linear Morse function, then the Morse inequalities hold when you let CQ be the number of PL critical points of a particular index, as opposed to just the ordinary critical points. And I think that's where I'm going to end for today. So basically, and I guess the sort of reason that this is useful for data analysis is if you suppose you have some crazy function, right? Then one way you might want to understand that function is you might have some height function that you're sweeping across, and you're understanding the homology of the topology of the shape as you sweep it across. This sort of filtration is analogous to the filtration you had when you have the check complexes, and we were just expanding the balls around each of the points. And so we're doing the same kind of thing. We get a filtration, and we can understand the topology of our data set in this alternate way, especially when our data has some sort of functional form and some sort of, where you can define some sort of height function. Yeah, okay, I think that's about it. Sorry if that, especially about my handwriting today. I don't know what's gone wrong with my handwriting, but yeah, thank you all so much. Tomorrow, I will be talking a little bit, I will be giving a sort of demo presentation on Hyperman hash in the first half, and then going through some of the proofs in the second half. And you guys should be working on your presentations. The homework is also up. So there is one more real homework that is due next Wednesday. It's very basic algebraic topology, very, very basic. So I don't expect you to need to spend too much time on it, which hopefully you shouldn't, because you guys need to be preparing your presentations for next week and the following week. Any questions? Class is dismissed.